Okay, often we have a situation where we repeat some experiment many times. This could be in sports or in gambling or in the laboratory, and we write down the result of each successive experiment or trial, and then we want to compute based on all these results. Um, if we can assume that these sub-experiments are independent, meaning that the outcome of one does not affect the outcome of another, which is certainly reasonable in many things like gambling, like say flipping a coin or playing the roulette table, um, then we can call the sub-experiments trials. Not that calling them trials gets us anywhere, but we can recognize that we can use the properties of independence. In particular, we can multiply probabilities. We can multiply probabilities to compute probabilities of intersections. So it just makes the calculations simpler. Okay, so all those conditioning things, P of E F equals P of E given F times P of F, just become P of E F is P of E times P of F, right? All right, so let's do an example. So let's flip. Let's just start with something like an example. So flip a coin, and we'll go slowly 6 times, and note head or tails each time. Find probability of EI, where I is 0 to 6, and EI is I heads occurred. Okay, let's do this very slowly and carefully so we can see the theory. This is something that's very important the rest of the course, so I just want to go very slowly and carefully this early, and then we will stop going so slowly. So what we can do is let's let HI equal the event that we got heads on flip I. So that would be for I 1 to 6, right? 1 to 6. Okay, and we note that because of the independence of the flips, that any sequence of heads, can be calculated by multiplying the individual probabilities. Yeah, but I'm jumping the gun a little. Let S be all sequences. Let S be the sample space of the big experiment, which is the 6 flips, is all sequences of the 6 flips, of outcomes on the 6 flips on the 6 flips. Okay, so to be clear, for example, H1, H2, H3C, H4C, H5, CH6 is an outcome, although maybe I'm writing it as an event like this, but this is also an outcome in S, and we see that the size of S is 2 to the 6th power. So there's 64 different outcomes. All right. So let's compute the probability of each result, of having no heads, 1 head, etc. So we also, does it say to assume they're independent? Let us flip a coin 6 times and know if I'm... Okay, so we'll write it now. I'll keep this here. So assume flips are independent and coin is fair, meaning probability of H2 equals probability H2 complement equals a half. All right, so then to compute P of EI, P of E0 then, no heads. All right, well, E0 is just one outcome. This is just P H1 complement, H2 complement, H3 complement. Okay, but by independence, and independence, the complements are also independent, I just have P H1C dot 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 P H6C. This is by the independence of the trials. Okay, any subset I can just multiply and I can do that. Okay, well, we just said the coin is fair, so these are all a half, so this is equal to 1/2 to the 6th power. Okay, what about PE1? What's the probability there's one head? Okay, well, the size of E1 is equal to all the choices for me to put a head here instead of tails. So there's 6 possible spots for the heads. So this is actually 6 choose 1. There are 6 outcomes with one head, right? So E1 has all 6 of those. And each one has the same probability, right? So let me just write E1 just so you can see this is equal to, it would be like H1, this one could be head. What else? It could be H1 complement, H2 could be here. I should have picked a smaller number, right? Okay, complement, dot, 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 to the last one, right? So, but the size is 6, we see. So to compute the probability of E1, I can write probability of E1. Each one has a probability, each of these has a probability of 1/64, and there are 6 of them. So probability of E1 is just equal to the probability of H1, H2 complement, H3 complement, H4 complement, plus probability H2, H1 complement now, H2, H3 complement, plus dot, 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 up until the last one, right? So there are 6 of these. And this is by ME. This is by ME. We can add these. But there are 6 of them. So I already knew that. But I wanted to go slowly so that you saw that what I need to do is to, I want to make sure. Yeah, what I need to do is add them because they're mutually exclusive. I can't have this event and this event. So there are 6 of these. So PE1 is just equal to 6 choose 1 times the probability of each of these, 1/2 to the 6th. So this is 6/64. Okay, we can proceed now in this way. I'm using both here. I'm using the independence to compute the individual probabilities, right? And then I'm using the mutual exclusivity to add them. So PE2 How many elements are in PE2? 6, choose 2. And they're all a half to the 6, so I get 15 over 64. PE3. So this is 20 over 64. Okay, and going the other way, we get the same thing, right? PE4 is the same as PE2 because of the half, right? Tails have the same chance as heads. And PE6 is the same as PE0. We can make a little picture here of the results before we stop for this one. I have a little bit here at 0. And let's see, it's 6 times that here. 1, and it's, I don't know if this doesn't look right, but okay, so if I took these, added these up, this is 20 over 64. So just these three, right? We have, if I say, what's the probability you have between 2 and 4 inclusive heads? You would say 50 over 64. That's quite a bit, right? And then okay, we're almost out of time for this one. We'll later see, actually, in the next section that this, in the limit, will approach the normal curve. For now, it was just to point out how to do this problem. So I'm going to do another one example like this where its probability is not a half, and then we have a few more problems to do with independent problems that have like trials, sub-experiments, independent sub-experiments.